Okay, so in the second part of today's lecture, we talked about the indexes. So firstly, we discussed about how indexes, what are indexes. So for example, in index 1, we have the index field that corresponds to the ID, and so for every single ID over here, it points to a specific record in the table. And for index number 2, the index is on the department, and in this case there are multiple pointers. Then each corresponding pointer will point to the relevant record in the table, and for computer science, it will point to all the records that are of the computer science. So this is just an example of indexes of a database. What then is the motivation for indexes? So let's assume that we have the record, we have the database that we talked about earlier, and that there are 88 records in the database. So assuming that we have 64 bytes for each record and 512 bytes for a block, we store 8 records in the block. And so for 88 records in total, we will need 11 blocks. And if we want to extract any record, it will mean that we need to search for all 11 blocks. So it is definitely a long time, or rather not efficient way to do it. And so to reduce time, we use an index. How then does this index work? I'll explain on that later on. So there are different types of two different types of indexes. So the first is on ordered indices, based on the sorted order of the values. The second will be based on the hash, which what we talked about earlier. We wish that the hash value will be as uniformly distributed as much as possible. So there are 5 evaluation factors for this: the access type, the access time, insertion time, deletion time, space overhead. And so so this will be how we evaluate how good or how bad the indexes are. We'll go into a bit of detail over the next few slides. So for SQL, for index for SQL, so the index key, which is automatically generated, there is automatically an index that's being generated for the index key. If I'm not wrong, even for the primary key, there's also an index that is being automatically generated for SQL. So what we have on top is we have primary key, candidate key, super key. These uniquely identify the tuple. Why is this important? Is because later on in the next lecture we will find out, or rather later on the lecture on Friday, you will find out this will affect the cost of searching for a record, whether is it the primary key, candidate key, or is it a non-primary key. So that will affect how costly the search is. But we will get there later on Friday, which is later on today. So there are 2 indexes that we want to focus on. The first one is primary index. Second one is secondary index. So the primary index is when the index also defines the sequential order of the master file, and the secondary index is when it is in non-sequential order. So I will add on an example to clarify this. So let's look at this table. If the index is built on ID, then this ID will be the primary index. Why? Because there is a sequential order of this database on the record ID. And if the database is built if the index is built on department name, there is no sequential order of this, and so this will be a secondary index. So let's assume that the ID is a candidate key and the index is being built on department. So is that considered a primary or secondary index? So if your answer is primary, then you should be correct. Why? Because you notice that this table is arranged in alphabetical order according to department. So department is in primary order, and department is in alphabetical order. And so even if department is not a primary key, but because it is in alphabetical order and you set the department column to be as an index, it will be considered as a primary index. Now we're going to look at the type of indexes. So this is a dense index that you see. So every single record is being linked to an index. Notice one main thing, which is the columns on the very right. So there is a pointer that points one record to the other, and this kind of links the order of the index from one to the other. So I will assume that if I were to insert a record, let's say 33457, maybe the possible option is it will come all the way at the end, but the pointer will form the new sequential order. So it pertains to what we covered before in the first part of the lecture, whereby how do we insert a tuple into the database while maintaining the order of the database. So this is that for the dense index. In the second one, which is the dense clustering index, so notice that in this case the records are ordered according to the department. So hence the term of clustering. So there is a particular order on the records, and that is on the department. So the index is built based on the department, and what we notice is that it points only to the first record of the department per se. So for example, biology points to the first and also the only record on biology. Computer science points to the first record of computer science, and so on, so on. What we also notice is that at the very end, on the last attribute, it is a pointer that points on to the next. So even though we are building an index only on the first record of computer science, but because of this pointer at the end, it is able to bring us to all the records of computer science very easily. So this is it for the dense clustering index. In the next one is the dense non-clustering index. Notice immediately the difference. You don't have the last column of pointers anymore because you really don't need to. What it does is that when it builds the index keeps directly all the records that belong to that particular department, and hence it is called dense. So for example, computer science, it keeps the record of record 0, record 6, record 10, which are the 3 records that are in whose faculty is belonging to the computer science department, and does so also for biology, electrical engineering, and history. So it is dense because every single record links directly to an index value. So for the sparse index, so the index entry appears only for some of the search keys. So you notice in this table, the order that is being arranged in is the order of the first column. There is the pointer at the end which points to the next key, and definitely if I were to insert another column, another record here, this would try to rearrange itself to make sure that the ordering of the records will still be the same. So this, in a way, the criteria for sparse indexing is similar to that of the hash indexing, meaning that it must be as uniform as possible. So let's say if I have 10 records in the let's say if I have 100 records in my database, I will try as much as possible to have and let's say if I have 4 indexes, I'll try as much as possible to space them all out as evenly as possible, so that every index, in between every index, maybe there'll be just like 25 records. So main thing is we want the records to be spaced out as uniformly as possible. So going back to the motivation, how is data being stored in a disk? So as we said earlier, if we have 88 records, we will need 11 blocks. To reduce time, we use the index. How does the index work? So this index, let's say, has only 2 parts, 2 columns. One is the SID and one is the pointer, and let's assume that both of them is 2 bytes each. So in total, the size of the pointer will be 4 bytes. And now, because the size of a pointer is 4 bytes, we have 88 records in total. So altogether, we have less than 512 bytes to store the entire index, which is just 1 block. And so right now, if we want to search for any record, do we need to search for 1 block, 2 blocks, or 3 blocks? The right answer is 2 blocks. The first block we need to search, we search for the index key. The index excuse me. The index key will give us the block to go towards, the block where the record is being stored in, and that will be the second block that we will be searching. So right now, instead of having to search through 11 blocks, we only need to search through 2 blocks. So that is the purpose of the index. But that's not the only thing. What happens if the number of indexes becomes too large? And hence we then have to create a multi-level index. So if my index becomes really huge, we then have to create another index that indexes this index. But when you rotate this in the clockwise manner by 90 degrees, where you have index 1 like this, index 2 like this, you realize that this then becomes looks exactly like a B or a B plus tree. So that is then the motivation for us studying the B or the B plus trees for databases, because that is how our records are being stored as. So I understand that some of us have little background in this. So let's go to some some fundamental terminology. So we have the so-called B trees or B plus trees. They come from the family of trees. So on the left, we see a binary search tree. In the BST, we have the nodes on the left that's always going to be smaller than the root node, and the nodes on the right, or either the root or the parent node, and the nodes on the right always larger than the root or the parent node. So sorry, before I go on, this is considered to be the root node. This will be the intermediary nodes. You can term them to be the parent node of root 1 and node 1 and node 6. This is the child node as well of root 10. This is the child node of node 5. The nodes at the very bottom, they are known as the leaf nodes. Okay, so this is the basic introductory to BST. So on the right of this, we call this a multi-way tree. So a multi-way tree occurs when you want more than one key in the node. So you notice for BST, you only have one node one key in a node. For multi-way trees, you are able to accommodate m number of keys in the node. So for instance, in this multi-way tree, it is a 3-way tree. So m equals to 3. You're able to accommodate 3 keys in a single node. So definitely this will this helps in being able to flatten the tree. The only issue with m-way trees is that there are no rules whereby the m-way trees are being constructed. So in the very worst case, what you're going to end up with is going to be a tree that is going to be extremely deep. And in the worst case scenario, let's say if you have n records, the worst case would be you have a tree of length of depth of n, and it will be the same as doing a linear search. Okay, now we go ahead with the difference between the B and the B plus trees. So for the B trees, you realize that the nodes only appear once on the B tree. So P doesn't appear anymore, C doesn't appear anymore, and so if we have if this is the index of record P, the pointer would point from here all the way to the relevant record on your database or on your block. So that's not the same for B plus trees. For B plus trees, your your key value is repeated all the way down to the leaf. So at your leaf level, 37 appears on your leaf level, 65 appears on your leaf level, 84 appears on the leaf level as well. So this is the primary difference between the B tree and the B plus tree. Okay, so this is an example of a B plus tree. So n is equals to 4, where n is equals to the number of pointers. So there is a 3-way tree. So there are 3 keys in every node, and there are 4 pointers in every node. So Mozart holds that of the root node, and you can tell the keys are arranged in alphabetical order. So everything to the left is smaller than m. Everything to the right is larger than m. Okay, so this is how this table is being arranged as. So let's say we go to for the next slide. If n is equals to 6, this means that it is a 5-way tree, and there are 6 pointers at on every node. So the constraints will be that the root node can hold fewer than n by 2 pointers, but it must hold at least 2 pointers. Okay. So the rest of the terms, I don't think I want to go through that much. It is essentially this is we want to focus more on the database aspect. The good thing about the balance property of B plus trees, ensure that there is good performance for lookup, insertion, and for deletion. Okay, so this is an important example where we want to select star for instructor where name is Srinivasan. So what happens is, the first thing that will happen is this is already in memory. First you have to check s is larger than the m, and so it will take on the pointer number 2. It goes on to this node. Over here, it will choose that Srinivasan is greater than or equals to Srinivasan. So again, P2 will be selected, and it will go up to this node over here, and it will match and return pointer number 1, which goes to the gentleman Srinivasan. Okay, let's go. Let's try another one. Let's say if you are looking for cats, which is this person over here. So you will first realize that k is less than m. You'll go on to this node over here, after which it will realize that k is larger than g, and so this goes to this node, and at this node it does the scan and it finds k, this pointer number 2, and then goes to this record. Okay, I hope this is clear. Okay, so now we come to our example. So the size of a node is 4k, and the size of a search key is 12, size of a pointer is 8. There are 100 million search key values. So what it is actually trying to say is that the size of my search index is going to be 12 plus 8, which is 20 bytes. And for a size of my, let's say the size of my search key for my pointer is 20 bytes, and the size of my node is 4k, it actually means that I can hold 200 search key pairs in every single node, and my m is equals to 100 million. Okay, so if we go back to the binary search tree, rather if you recall, right, from what we study, if you did algorithms for binary search tree, the height of a tree is determined by the number of branches it has. So the height of a binary search tree is equals to log n base 2. So if you if my tree has 3 branches, it will be log n base 3. So in this case, right, it should, by right, I thought that it was log n base 200, because I'm going to have 200 sort of so-called pointers in my tree. But apparently the suggested solution is 100. So what I can only imagine why they put 100 is because the criteria for this this B plus tree is that half of the nodes need to be filled up. So I think they are doing an average case analysis whereby it is not the full 200 nodes that are being filled up, but just half of them, which is 100. And actually, I after thinking of it, probably, yeah, it does make a lot of sense. And so I'm going to go with that that line of reasoning, whereby I'm going to assume that only half of my intermediary nodes are being filled up, and so I will the fan out factor, or rather the number of branches each node has, is only going to be 100. And that being so, the height of the tree will then be log n base 100, which is what you see over here. Log n base 100 is going to be 4 nodes, and if the root node is already in memory, we only have 3 IO operations. Okay, so hope this clarifies this question. Okay, let's go on to the next question. So hash index, is it primary or secondary? So this pertains to the how the hashes are being built. So in what we want to say in this slide is that for bucket number 5, so notice that there is an overflow. There are only 3 hash indexes in bucket number 5, and one of the index points to the next hash bucket. So basically the bucket has already overflowed, and so it goes on to the next bucket. Okay, so this is mainly what we wanted to say for this. So ordered indexing versus hashing. So if you have a criteria whereby this is equals to something, you can do both ordered indexing or both hashing. Hashing would have a much better performance than ordered indexing usually. However, when you have queries like less than or greater than or less than, then you realize that hashing will not be able to work for this. So for example, if I want to find people whose pay is greater than let's say pay is greater than $85,300 a year, so it's really impossible for me to be able to come up with a hash function that will be able to represent that number incorrectly. So for range like this, this doesn't really work at all. Okay. So in practice, rather another example, is it possible to have two clustering indexes on the same relation for two different keys? So what this is trying to say is I have two clustering indexes. So remember, if we have clustering indexes, it means that these are all arranged in a certain order. So you're going to have like one key with, or rather one record with let's say department computer science, and all below be computer science. Another record, let's say is physics, and all be under physics. So in general, this will be not possible, because unless you're going to have two table, or rather two columns with exactly the same values, which is impossible. Yeah, so usually and they're ordered in the same way. So yeah, so in general, this is just not possible. I mean, this is just not possible. Okay, so another thing, I think this is the last question. So for the B plus tree, show the steps involved in the following queries. So for the search value of 11, so it's going to go to 19. It's going to find 11 is less than 19. It's going to go to this side, and it will search from here onwards. 5, 11. Then it realizes that 11 is this value. It's going to go to P3, come over to this, and does a sequential search. It's going to take P1. Okay. So this is it for the first question. For the second question, between 7 and 17 inclusive, so what is happening will be 7 comes here first, it goes to the left, and it will take this P1 over to this. You will look at P1, 2, and you look at this value P3. Next thing, you'll go to 17, then it will how to say, it will go on to the left side once again. Let's go on to pointer tree, come to here, and it will go to this pointer. So what will happen is this pointer is going to traverse to this pointer, to this pointer, to this pointer, all the way up to this pointer. Sorry, all the way up to this pointer, and to find out all the records from 7 to 17 inclusive. Okay. So I think this is the last slide. So once again, gentle reminder to provide your feedback. So I'll see you later on during the class today. Good luck for the quiz. Thank you.